Okay, so basically there are two things I would like to discuss before concluding the semester. Now, one is the Bell's inequalities. And the other one is the Wigner-Eckardt theorem. Now, let's start with the Bell's inequalities. What is it about? Now, if you consider, for example, just if we take two spin 1/2 particles, and let's say we create them in the state z plus, z minus, minus z minus, z plus. This is our state. And this is the spin of the first particle. This is the spin of the second particle. And then let's assume that you make a measurement of the spin of the first particle. And you get Z plus. So this basically tells you that your state, after this measurement, we had already seen that the wave function collapses, and the only component compatible with this observation is the first component. So now after this measurement, my wave function collapses into this ket. My initial ket is collapsed into this one. But this ket tells me that the second particle has a definite spin, the spin minus, after the first measurement. So it is already, we didn't make any measurement on the second particle, but now we are definitely sure that its spin is negative. As long as you are sure that you create this state to start with. In that case, you know that this is your state after the first measurement, and in a sense, the first measurement determines the spin of the second measurement. That's the spin of the second particle. So this was kind of weird. I mean, a couple of things that is weird about this measurement is that, I mean, before we were talking about the single measurement, single particle and the single measurement, we were measuring the properties of this particle, but now we have two particles, and although we are making, in a sense, a partial measurement, in the sense that we are only measuring the particle 1, it also influences the second particle. So although you are making a measurement on the first particle only, it is as if you are making a measurement on the whole system. Now, the second weirdness is that since we have these two particles, they can be anywhere. We didn't say anything about their position. For example, one can be here. One can be right at that point on the screen. And the other one can be, let's say, in a different galaxy, let's say 5 light years away. This is the particle 1, this is particle 2. And let's say the particle, before leaving, you just agree with your friend that you will make a measurement at A will make a measurement at a particular time. Let's say t equal to 0. The second one will make a measurement at t is equal to 0.1 second. So they are separated by 5 years. That's the next star, let's say, close to the next star. And the moment that you measure the position of the particle, the spin of the particle 1, you know what the spin of the particle 2 is at that moment. Well, it gets even weirder. You see, if you just take two events, one at t equal to 0 at a given point, the other one 5 light years away at the time t is equal to 0.1 seconds, you see, if you remember your course on special theory of relativity, it says that the simultaneity is a frame-dependent quantity, at least for certain events. Definitely it will be true for this one. In a given observer, those two events can be at the same time. In a different reference frame, the one event is before the second event. In a yet third reference frame, the first event is after the second event. So the time ordering of these events, if two events are not connected by, let's say, causality, if they are separated by such a what is called a space-like separation, their order in time will depend on the reference frame. So although we are in this reference frame, we are saying that A makes the measurement first, and that measurement determines the outcome of the measurement of B. Well, in a different reference frame, B will be making the measurement first, and then that will determine the outcome of the measurement in A, which, I mean, is kind of weird. And of course, Einstein didn't also like this idea. He was, I mean, in most aspects, he was against the quantum theory, although he helped a lot in its development. And this was one of the things that they didn't like, this kind of the action at a distance, let's say. So the events in A and the event in B, they are not causally connected according to Einstein. Nevertheless, they seem to somehow influence each other. Now, of course, the question one would really ask is, okay, this is just a, let's say, a thought experiment or a mathematical construct at the moment. Can it have observable use, I mean, physical uses? Like, can we transfer information from point A to point B using this thing? Because we know that if you make a measurement in A and you know the outcome, then you know the outcome at the point B, measurement at the point B. So can we use this to transfer information? Of course, if this would have been possible, it will also tell us that we can send information to the past. Because you see, event B is before event A in certain reference frames. So if we could send information, then this would have been, it would be, give us a way to call the past rather than the present. Sorry. Okay, so now the idea is that, let's say, you see, the point is how, if you are, let's say, B, you are making the measurement in B, and you have many particles, many identical particles that are created in this state. So what will be your measurement? So if you have, let's say, 1,000 particles in this state, if you make measurement of your second particle, 50% of them will show spin up, 50% will show spin down. And suppose, for example, the measurement in A decides to send one bit of information. By, for example, instead of measuring the Z component, it can measure, let's say, the X component. So if somehow this information can be transferred to the other side, you can basically, if the B can somehow determine that A was measuring X instead of Z, well, that would be like sending a bit of information. If A measures in X, let's define it as bit 0, and if it measures in Z, then bit 1. So if somehow the B measurement can determine in which direction the A makes measurement, so you are sending bits, you are sending information. But let's see, if A measures not the Z but the X. Well, we can write this state alpha, which was 1 over square root of 2, Z plus Z minus, minus Z minus Z plus. Well, we can just make a change of basis, and this state just becomes x plus x minus, minus x minus x plus. Now let's see. Let's say A measures x to be plus. Let's just make an assumption. Well, then alpha after the measurement just becomes x plus x minus. And B keeps on measuring the Z, but it will still measure 50% Z plus 50% Z minus. Nothing basically will change in the measurement, in the outcomes of the measurements made at B. In fact, no matter in which direction the A makes measurement, you see the alpha ket we can always write in this form, n plus, n minus, minus n minus n plus. So measure n to be plus. Well, this would mean that after the measurement, the system has a ket n plus n minus. And the measurement of the B will be well, yeah, okay, so let's look at in a slightly different way. So, it will be measurements in A will be 50% n plus of the first particle and 50% n minus. Now, if it is n plus, the other other particle is n minus, and if it is measuring the Z component, so it will obtain with cosine squared theta Z plus with sine squared theta as Z minus. You see cosine squared and theta being the angle between n and Z. But this is, of course, will be, okay, this has probability 1/2, this has probability 1/2. And if you look at, if it is n minus, it will be sine squared theta and cosine squared theta to be Z 1/2, this is Z minus 1/2. Now, of course, it seems to be changing, but keep in mind that, I mean, the other particle makes measurement in everything. So, in total, the A makes a measurement, the probability that it will measure a plus measurement is 1/2. Then the probability that the other particle will make a measurement Z plus is cosine squared theta, plus the probability that A makes a measurement of n minus is 1/2, and then the probability that the others will make a measurement of Z plus will be sine squared theta. in total 1/2. The measurements in B, with 50%, it will release 1/2. With 50%, it will release minus 1/2. So in whichever direction you make a measurement in part A, the outcome of part B never changes. So no matter what kind of a measurement the second you make on the second particle, there's no way that you can determine that A made a measurement and what the outcome was. So basically what you will see is you make a measurement at A, then somebody else makes a measurement at B. Only if you bring these two information together, you will see that they are strongly correlated. In the sense that, let's say, both measure in the Z direction. When you bring these two information together, you will start seeing that if one measured plus, the other one measured minus. If one measured minus, the other one measured plus. Before that, there's no way to determine what the other's measurements were or what they measured. Hence, no transfer of information. Of course, there is still the problem. It's kind of weird in the sense that on one hand we say that, okay, quantum mechanics is not local in the sense that what you do over here, it does influence what is over there, according to the quantum mechanical description. But on the other hand, it is also kind of local, because unless you bring them together, there is no way that you will be able to know that there was this non-locality. But of course, Einstein and, well, I don't think anybody likes this idea of action at a distance in quantum mechanical interpretation, but that is probably one of the best explanations we have at the time being. And people were looking at maybe there are some other properties of the system that we are not measuring, but somehow will determine what the outcome will be. And before the particles send away, before we make the measurement, some of these variables, they do determine what the outcome of each one of the measurement will be. And when you do the measurement, you see this correlation, but not because they influence each other quantum mechanically, but because there are these other parameters which we are not aware of, which determine the outcome of the measurement before we make them. This was one of the ideas, so-called the hidden variables. So basically they say that, okay, all these quantum mechanical uncertainty, etc., they arise mainly because we don't know enough information about the system. There's some other information that the system contains that we are not aware of. Now let's consider such a system. Now let's consider that we will make some measurement of the spin in 3 different directions. Well, okay, before that, let's start with 2 directions. Let's say that the Z component of the spin is plus, the X component of the spin is minus. Maybe it's already determined somehow what the outcome of the measurement is. Okay, you see, when I'm talking about Zx minus, this is still the first particle, this is the second particle. I still don't want to discuss about the okay, no, I can still say that, sorry. This is for one particle. Okay, there are these additional parameters which determine that the Z component of the spin will be plus, and if I measure the X component, it will be minus. Of course, we have pairs, and we know that initially we created a system with spin 0. So this should be paired with a Z minus X plus particle. So this is particle 1. This is particle 2. Or, I don't know, whichever direction you like, Y minus X plus. This should be paired with the second particle, Y plus X minus. so that the total will be spin 0. Now the fun kind of begins when you have 3 axes, A, B, and C. So somehow, before we make measurement, you see, the problem is this one, the problem that we are trying to address. If the spin of the particle is not determined before we make the measurement, we have one system over here, one system over there, and none of their outcomes is determined before we make the measurement. To understand, to explain this correlation between the measurements of A and measurements of B, we should assume this non-locality that once you make the measurement here in your first system, the wave function of both of the system collapses, and then you know the outcome of the second system. If the outcome of the measurement is not determined before you make the measurement, you just cannot avoid non-locality. The only way to avoid it is to assume that once you create the system and then you make measurements later on, the outcomes of the measurements should be determined at the moment that these 2 particles are created. So they are already correlated, the outcomes are correlated no matter how far away they are. So that's basically the idea. If the outcome is already determined, then we end up having some inequalities. So that will be what we will call Bell's inequalities. And these kits, these ABCs, I will just, this is particle 1, this is particle 2, the measurement of A, B, and C, the measurement of A, B, and C of particle 1 and particle 2. Well, basically we have 3 possible choices, plus, 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 this will be minus, 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 plus, plus, minus, 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 plus, plus, minus, plus, minus, plus, minus, plus, minus, 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 plus, plus, and minus, plus, 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 minus, 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 plus, minus, plus, minus, plus, minus, minus, plus, okay, plus, plus, minus, and minus, 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 plus, plus, plus. These are the possible outcomes. And we have many particles who the outcome of the measurements is, if we assume that they are already predetermined at the moment that they are created, and they are determined by some kind of a variable that we don't know, some dynamics that we are unaware of, but whatever the dynamics is, they determine what the outcomes should be. That's our assumption. And then let's say that this will be N1, and 2 of them will have this configuration, and 1 of them will have the first configuration, and 3, and 4, and 5, and 6, and 7, and N8. Now let's look at this one. What is the probability that if I make a measurement, let's say on the properties of particle A, that I obtain A plus and also B plus? Well, if both of them are plus, I only have N1 and N2. So in N1 plus N2 of my particles, both A and B, they are plus. Let us divide by NT. But I can also write this in this form, or let's say less than or equal to N1 plus N3 plus N2 plus N4. Now, why did I add N3 and N4? look at N1 and look at N3. If you look at N, well, this inequality definitely holds because N3 and N4, they are larger than or equal to 0. They are just numbers. They can be 0 or larger than 1, so I'm basically adding a non-negative integer to N1 plus N2 on the right-hand side. So the number gets larger. That's why I have the less than or equal to sign. And if you just look at the N1 and N3, you see they are both A and C plus. This should be less than or equal to, the first one is the probability that A is plus and C is plus. The second term over here, N2 and N4, is that the probability that A is plus and C is minus. So this is what's called the Bell's inequalities. Yeah, inequality. If you violate this, then you cannot claim that the outcome of the measurements are determined before you make the measurement. Because if the outcome is determined before, I mean, this is just assuming that the outcome is determined before you get such an inequality. If this inequality is not satisfied, then you cannot claim that the outcome is predetermined. Well, okay, this is what's called a no-go theorem, in the sense that here we are not really assuming anything about the model. We are just assuming that it determines the outcome of the measurement, whatever model you have. And if it determines the outcome of the measurement, then you have such an inequality. So if this is violated, then the outcome of the measurement is not determined before. Well, there are a couple of loopholes. Well, one of the still remaining loopholes, if you buy it, let's say, is that, you see, if you look at physics, the laws of physics, except on the measurement, and let's say, let's assume that we don't, I mean, in the problem of the measurement is that we are assuming that we as intelligent beings or whatever is making the measurement is classical, is not subject to the dynamical evolution of the quantum mechanics. There's no superposition in the measuring process. Now that is kind of problematic. How do you make this separation in nature? So one way out is to say that, well, everything is subject to a quantum mechanical description. There is nothing outside and has no measurement, actually. But that means even the quantum mechanical time evolution is deterministic. Well, Newtonian mechanics is already deterministic. So it basically tells you that given the initial condition, everything is fixed already. Of course, it brings the problem of the free will. Are we really making free choices? Or our choices are already determined before? So this measurement kind of says that if we have the free will, let's say, that we are creating this, we have decided to create such a system, then we have this inequality, and if this inequality holds, then no problem. If this doesn't hold, then the outcome of the measurement is not determined beforehand. But it might be that, well, maybe everything is determined since the beginning of the universe. Also, which measurement we will make is also determined, the outcomes are all determined, etc. So in such a case, you can kind of avoid this Bell's inequality problem, but that's kind of a, let's say, not so fun interpretation. We like to think that we have free will, and we are making choices. So let's just ignore that loophole for the time being. And so this is the inequality we have. Now let's look at our system. we had this system. Let's assume we have 1 over square root of 2a plus a minus plus or minus the probability that is a minus a plus. Now this is my system. And at the point A, you make a measurement. And let's say you have measured a plus. Then we know that the other one will be a minus. Or let's say a minus. So after the measurement you have this skid. So you know that it is a plus. Now what is the probability that if you have a plus and then you measure b plus, and a and b are just basically different axes? Well, this probability, you see, if this is our axis A, this is our axis B, they are at an angle theta. Now we had already studied this. This is, okay, so let me just change my argument slightly. I have these three axes. I measure a plus in the first particle and b and c in the second one. So this is particle 1. This is, let's say, particle 2. Well, this will be just cosine squared theta over 2. Let me call it theta AB. You see, initially the spin of my particle is in the negative direction, so this is the angle I have, pi minus theta. And this 1 over 2 is because I have spin 1/2 particles. So this will be just sine squared theta AB over 2. Now if I start with my initial particle, initial state without any measurement, the probability of measuring a plus is 1/2. If I measure a plus, then the probability of measuring b plus is just sine squared theta 1/2. So this is the first probability of measuring a plus first. Then we can work out the probability of a plus and, let's say, c plus. This will be 1/2 sine squared AC over 2, and then probability of a plus now hold on, I'm probably making some mistake. Okay, so let me just go back again. Let me just start from the beginning. Okay, I have these two particles. I have chosen these three axes, A and B. Now, what I'm going to do is the probability that the first particle is A plus, and the second particle is B plus. Okay, so this is, okay, A is plus and B is plus is I have N3 and N4. So the first probability is for the first particle, the second probability is for the second particle, the second second measurement. And this probability is the probability that the first particle I measure plus and the second particle I measure also B plus. And those two are just A plus and B plus. A plus is the first two rows, and this is the B plus row. And then I will write it as the probability of A. Well, let's look at the A plus and B plus are these two. So let's see, this is A plus and C plus and 4. A plus and C plus is N4 and N2 over N total plus, let's see, N3 and A plus C minus is N3 and N1. Okay. Now this is the final thing I have. Again, I repeat, the first A plus is the outcome of the measurement of the first particle, B plus is the outcome of the second argument is the outcome of the second particle. And if we come back over here, the probability that I measure A plus on the first particle and B plus on the second particle is, okay, the probability that I measure A plus in the first particle is this 1/2. Well, if I measure A plus in the first particle, then I know that the second particle is in the state A minus, so this is its spin direction. And the probability that it will be observed as a B plus in the B direction will be just sine squared of theta AB over 2. Now we can look at the other probabilities. If you look at over here, I need the two other probabilities. Is A plus C plus is just the same expression with theta AC, angle between the A axis and the C axis, and AC minus okay, let me make one more correction over here. So let's say AB, okay, this is true. So we have AC plus and, okay, this inequality is also correct, by the way, but we should be looking for something else. C plus and B plus. Well, is that true? Let's see. What's the probability of A plus and C plus? Well, A plus and C plus is N2 and N4. C plus and B plus is not N1, N3 and N7. Now the previous result, as I said, was also correct, but that just didn't serve our purpose in this discussion. Okay, so We already know PAB, PAC plus is, this is the correct expression, PC plus and B plus will be just similarly 1 over 2 sine squared theta BC over 2. So basically what Bell's equality in quantum mechanics, what quantum mechanics tells us, and if we believe in Bell's inequalities, sine squared theta AB over 2, this should be less than or equal to sine squared theta AC over 2 plus sine squared theta BC over 2. Now let me put a question mark. If I just use these probabilities that I calculated using quantum mechanics into the Bell's inequality, let's see, I can choose theta AC to be theta BC to be 45 degrees, and theta AB will be just 90 degrees. Now, what is sine of 45? Sine squared of 90 degrees over square root of 2. This should be equal to twice sine squared of 45 degrees over 2. Sine of 45 is 1 over square root of 2. So a square is 1 over 2. This should be less than or equal to, let me subtract minus 1, add 1. This is 1 minus cosine 45 degrees. 1 minus 1 over square root of 2. The left-hand side is 0.5. This is approximately 1 minus 0.7, which is 0.3. So 0.5 is less than or equal to 0.3. Of course, in quantum mechanics, such an inequality does not hold. You see, what we had said before was, okay, let's assume we have such a hidden variable theory. It can be very complicated such that it can account for our observations for a given particular system, all measurements. But whatever you do, if you just compare two measurements of entangled systems, you should end up, whatever that complicated theory is, you should end up having such an inequality. If there's such a hidden variables which determine the outcome of your measurements beforehand. And we didn't even, by the way, really make measurements of two incompatible observables. We just make one measurement in particle 1 and a separate measurement in particle 2. And if we work the quantum mechanical machinery, we had seen that at least in this particular case, you measure the spin in this direction, and in this direction, 3 different coordinates with 3 different directions. And we had seen that these quantum mechanics predicts that this inequality should be violated. It cannot be violated in a theory which determines the outcome of the experiments beforehand. But in quantum mechanics, it is. This is something you can measure and you can determine whether the inequality holds or not. And it turns out that these Bell's inequalities are not satisfied in actual experiments. And in a way, we basically know experimentally that the outcomes of, well, there's a very small loophole, which for that loophole you have to assume that everything was determined at the Big Bang, there are no choices, etc. But if you accept that you have some kind of a choice to make some measurements or not, here you are choosing which directions to use to make your measurements, and you are choosing how you are creating your system, etc., then we now know that the outcomes of the experiments are not predetermined when you are creating them. They do influence one another. Not in a way that we can send information, but nevertheless there is an influence of whether you make a measurement in this system over here, it influences the outcome of the measurements out there. And this influence you determine when you just bring them together and compare your results. Any questions? Okay, let's give a break now, a 10-minute break, and then we can continue.